Hey mathematicians, as you are annotating your graphs with the key vocabulary words, I wanted to give you a couple of special notes, especially for those of you guys that weren't here. So, when you're reading a page on a book, typically you start on the left side of the page, right? And then read to the right. Obviously, I'm not talking about manga, just talking about, a standard American book. So graphs are exactly the same way. You start by reading them on the left-hand side and then use whatever it's doing moving to the right to demonstrate their behavior. So for example, since this graph starts on the left-hand side here, and because as you move to the right, it's going down, this would be an example of a graph that is decreasing because from right to left, it is going down. And another key component of this graph occurs in two different places. One occurs right here, and it is called the Y-Intercept. And this is just the place on the graph where the graph hits the Y-axis. So you can see right there, the graph hits the Y-axis in that spot. And what does this aspect of the graph represent in real life? Well, it represents the fact that Grayson was 75 feet above the river before he actually jumped. So he hasn't actually jumped yet, right? So another term we use for this is the initial value, okay? These two things mean exactly the same thing. Initial value is just a way of saying this is where he started before anything has actually happened. He's 75 feet above the river before he actually jumps. So no time has actually passed yet. So let's compare that to another key component that's on the graph right here down at the bottom. And this time, because this is where the graph hits the x-axis instead of the y-intercept, this one is called the X-Intercept. So what does this actually represent in terms of the real life situation? Well, for our terms here, we can say that in this situation, the X-axis kind of represents the level where he hits the water, right? So a lot of us consider that his elevation, so his feet above the water, is now going to be 0. Because he's now, at sea level. So these are a couple of important key characteristics that you can find on this graph. Something else that I wanted to point out to you, so on the fish tank example, remember in class we talked about even though both graph H and graph D represent an amount that is decreasing in both cases, the reason it was graph H instead of graph D is because of this part right here where it says it was drained, the water was drained at a constant rate. So whenever you see an increase or a decrease at a constant rate, it's going to make a straight line just like this. So that's why it couldn't be graph D, because while it's decreasing, it's not decreasing at a constant rate, and you know that because it doesn't make a straight line. So this particular graph has a bunch of different words that could go along with it. It's got, for starters, we've got that constant rate of change, which I'm going to abbreviate it just like this. So we're going to abbreviate it with the word CROC, okay, for constant rate of change. Something else that I didn't discuss on the last graph but applied to it, but I'm going to go ahead and talk about here, is that this y-intercept, first of all, we can see there's a y-intercept there. I'm going to color code that in the orange because I do have a y-intercept. And then this aspect of the graph is also something called, so right here is also a maximum because it was his highest point. And then, of course, another word that we would use to apply to this one is that it is decreasing. So this one has a lot going on with it. I should make a special note here that it does have a maximum, and you may want to go ahead and be tempted to write the word minimum in this graph too, because, I mean, we know in terms of real life that eventually, you know, that fish tank is going to run out of water, right? But I'm going to stick to what this graph officially says, even though mathematically, it's not 100% correct. So that arrow right there implies that it's going to go forever and ever and ever. Even though, again, we know in real life, there's only 200 gallons of water in this aquarium, but we're going to stick with the graph features for right now. So since there's an arrow there that implies that it's going on forever and ever, we're not going to label it with the word minimum for right now. Finally, the last special note I wanted to make can be found right here on graph G. And for graph G, you can tell that obviously this one is not decreasing like the last couple we just talked about. This one is in fact increasing in a couple of different places. So right there. And these two line segments would also represent a constant rate of change because it is increasing at a constant rate. So again, I'm going to abbreviate that with CROC. And another word that I haven't talked about that's on our vocab list is anytime you do have this constant rate of change, it's also going to result in something that is linear because it forms a straight line. So these two line segments actually have 3 different vocabulary words that go along with them. They're a constant rate of change, they're increasing, and they're linear. Now let's talk about this little segment in the middle because I haven't done anything with that one yet. I'm talking about this that's in kind of like the little fuchsia. So in terms of the situation, remember he's on the ski lift and then, you know, he was going up, but now apparently they've hit some kind of a snag so the ski lift is stopped for several minutes. So this no longer represents a constant rate of change because the height is not actually changing. This is simply something we call constant. I'm going to actually write it over this little segment here. So it's not going to be a constant rate of change because the height isn't actually changing. It's staying the same for that amount of time. It is, however, still linear also because it does make a straight line. It's just that it's not a constant rate of change. In this graph, we also have a minimum. So I'm going to label that. And because the minimum is sitting at the origin, it actually has an X and a Y-intercept. So anytime the graph hits at the origin, it's got both an X and a Y-intercept. And then because this arrow is up here at the top, which implies that it's going to keep going forever and ever, we obviously know that in real life, the ski lift wouldn't actually be going, constantly forever and ever and ever. But because there is an arrow on that graph, for intents and purposes for here, I did not say that very well. We're to stay consistent with the graph, we're not going to mark that as a maximum. We're just going to assume that arrow is true, even though we know in real life, that ski lift isn't going to keep going. So this kind of concludes all the special notes I have about this. Oh, you guys don't need to worry about doing that last one about the jelly bean. Don't worry about that one. But please take the time to go through and annotate your graphs with all of the vocab words that would be applicable because we are going to be having a quiz over this fairly soon. Let me know if you guys got any questions.